Most people think the James Webb Space Telescope was built to confirm what we already know about the universe. It wasn't, and what it actually found has caused a Nobel Prize-winning physicist, a man who has spent his entire career measuring the cosmos, to say something that should stop every one of us cold. He said, "Our picture of the universe is probably completely wrong." Let me tell you about Adam Riess. He is not a fringe scientist. He is not a YouTube theorist with a green screen and a dramatic voice. He is a Nobel Prize-winning physicist at Johns Hopkins University, one of the most decorated cosmologists alive, and in 1998 his team made one of the most shocking discoveries in the history of science. They discovered that the universe is not just expanding. It is expanding faster and faster, accelerating, like a car that someone pressed the gas pedal on and never let go. That finding was so unexpected, so completely outside what anyone had predicted, that it earned Riess and his collaborators the Nobel Prize in Physics in 2011. This is a man who is not easily surprised, which is exactly why, when he sat in front of his own data in late 2024 and said 4 words in plain language to the scientific community, the entire field paid attention. Not a theory, not a cautious academic suggestion buried in footnotes. 4 words stated directly. We have misunderstood the universe. He wasn't being dramatic, he was reading his instruments. And I'm going to tell you exactly what those instruments showed him. But before I do, you need to understand the number that started all of this. Because this isn't a story that begins with James Webb. It begins almost 100 years ago, with a measurement that turned out to be one of the most contentious numbers in the history of science. And it has never been fully resolved. In the 1920s, an astronomer named Edwin Hubble looked out at distant galaxies and noticed something remarkable. They were all moving away from us, every single one, in every direction, and the farther away they were, the faster they were moving. The universe was expanding. Hubble calculated the rate of that expansion and gave it a number, now called the Hubble constant. It is the single most important number in cosmology. It tells us how fast the cosmos is flying apart right now at this exact moment, and from it we can derive the age of the universe, its size, its ultimate fate. Hubble's original estimate was so far off that it made the universe appear younger than the Earth. For decades after, 2 camps of astronomers fought bitterly. Some believed the true value was closer to 50, others closer to 100. A disagreement so fierce it split the field in half. By the early 2000s, the number had finally converged. After decades of argument, everyone agreed. The Hubble constant was somewhere around 70. The war was over. Except it wasn't, because as instruments got more precise, a new split emerged. Smaller than the old one, but far more stubborn. The first modern measurement comes from looking backward. The European Space Agency's Planck satellites spent 4.5 years mapping the cosmic microwave background, the faint afterglow of radiation left over from when the universe was just 380,000 years old, a fingerprint of the Big Bang itself. From that map, physicists extracted the conditions of the early universe, plugged them into the Standard Model, our century-old framework for understanding all of reality, and ran the equations forward nearly 14 billion years to predict how fast the universe should be expanding today. Their answer: 67 kilometers per second per megaparsec. A megaparsec, by the way, is 3.26 million light-years. So for every 3.26 million light-years you look outward, galaxies are receding 67 kilometers and faster. Clean, tiny margin of error, confidence level through the roof. The second measurement is more direct. Adam Riess and his team, called CES, measure the present. They built what's known as the cosmic distance ladder, starting with pulsating stars called Cepheid variables, whose brightness fluctuates at a rate directly tied to how luminous they actually are. Measure the pulse, calculate the true brightness, compare it to how bright the star appears from Earth, and you have a precise distance. From there, they step outward to galaxies containing both Cepheids and a specific type of exploding star called a Type Ia supernova. These supernovae are useful because they all explode with roughly the same peak brightness. Spot them in galaxies hundreds of millions of light-years away, and you can calculate those distances too. Combine that with how fast those galaxies are receding, and you get the Hubble constant. Riss's answer, not 67, 73, 73. Now, 67 versus 73. On the surface, that sounds like a rounding error. A minor academic squabble between two groups of scientists who need to get out more. It is not. In a field where measurements are routinely precise to within 1%, a gap of 8 to 9% between two completely independent methods is enormous. It is the difference between a universe that is 13.8 billion years old and one that could be more than a billion years younger. It changes the size of the observable universe. It changes the rate at which galaxy clusters are separating. It potentially changes the very nature of the dark energy that has been pushing everything apart since the late 1990s. Think about what that actually means for a moment. If the universe is expanding faster than our best model predicts, then everything downstream of that prediction shifts. The age of the universe, the distances between galaxy clusters, the timeline for when the first stars ignited, when the first heavy elements were forged inside dying suns, when the conditions for planets and chemistry, and eventually life became possible. You're not adjusted dial on a dashboard. You are potentially redrawing the entire history of everything that has ever existed. For years, scientists assumed someone had made a mistake, and the leading candidate for that mistake was called stellar crowding. Cepheid variables tend to live in the dense, dusty disks of younger galaxies. When Hubble looked at them, its cameras sometimes blended the light of nearby stars together, making the Cepheids appear brighter than they truly were. Brighter Cepheids mean shorter calculated distances. Shorter distances mean a higher Hubble constant. If you could clean up that blending, the theory went, the tension would relax. The two answers would converge. So Raius pointed the most powerful telescope humanity has ever built at the same stars, and waited. The James Webb Space Telescope orbits the Sun approximately 1.5 million kilometers from Earth, far beyond the interference of our planet's atmosphere and thermal radiation. Its 6.5-meter gold-plated mirror collects infrared light with a sensitivity that makes Hubble look like a pair of reading glasses from a petrol station rack. If any telescope in human history could settle the Hubble tension, it was Webb. The expectation among most of the field was clear. Webb's sharper infrared vision would cut through the dust and crowding. The Cepheids would look different, dimmer. The distances would stretch, and the Hubble constant would drop back towards 67. Some astronomers were already drafting the obituary for the crisis before the data came in. That is not what happened. In early 2024, the SHE's team published a paper in the Astrophysical Journal Letters. They had used Webb to span the full range of Hubble's Cepheid observations, extending all the way out to a galaxy called NGC 5468, approximately 130 million light-years from Earth. 1,000 Cepheids across 5 host galaxies, 8 supernovae, cross-checked with carbon-rich stars, and a technique called the tip of the red giant branch. The Cepheids looked the same. The distances held. The expansion rate stayed at 73. 3 separate methods, 3 independent confirmations, all pointing to the same answer that the standard model says is impossible. Raius stated the conclusion with characteristic precision. With the errors eliminated, what's left is the possibility that we have misunderstood the universe. At a conference at the Kavli Institute for Theoretical Physics, Nobel laureate David Gross corrected the language being used. They shouldn't call it a tension, he said. They shouldn't even call it a problem. Call it a crisis. When Webb launched, scientists had a very specific picture of what the early universe should look like. Small galaxies, dim ones, loose, scattered clusters of primitive stars just beginning to collapse under gravity. Simple infant structures in a young, violent, chaotic cosmos. The standard model was explicit about this. The early universe simply had not had enough time to build anything large or complex. That was the prediction. Then Webb found GZ9P3, a galaxy that existed just 510 million years after the Big Bang, in a universe that is 13.8 billion years old, that is like finding a fully grown, educated, experienced adult in the delivery room, still wet, already wearing a suit and carrying a briefcase. GZ9P3 was not dim, not small. It was 10 times more massive than other early galaxies Webb found from the same period in the universe's history. It already showed complex internal structure, a double core, suggesting two separate galaxies had already found each other, collided and merged. Inside, Webb found young stars born directly from that collision, only a few million years old, sitting alongside a completely separate, older population of stars already over 100 million years old. Stars that had been growing long before the merger even happened. The galaxy had a history before its most dramatic event, and Webb's spectrometer, a tool that breaks down light the way a prism breaks down sunlight, detected silicon, carbon and iron within this ancient galaxy. Iron, the heaviest element that stars are actually capable of producing. Forged inside massive stars through billions of years of nuclear fusion, then scattered across space when those stars died in supernova explosions. In a universe that was barely 500 million years old, think about the chain of events that requires. Stars had to form, burn through their hydrogen, fuse helium into heavier and heavier elements, run out of fuel, explode, scatter those elements across the cosmos, and then those elements had to gather again into new clouds, new stars, new galaxies. All of that had to happen, start to finish, in under 500 million years. The standard model says that should take billions. Astronomer Mike Boylan-Colchin ran the numbers. He showed that 6 of the earliest and most massive galaxy candidates observed by Webb pushed right up against the absolute upper limit of what the standard model allows. To form galaxies that heavy, that fast, nearly every available atom in their surrounding dark matter halos would have had to convert into stars. In a normal universe, that conversion rate sits around 10%. 90% of the gas never gets around to forming anything. It's too hot, or it gets blown out by radiation, or it simply drifts. These galaxies appeared to be running at 100% efficiency, like a factory that somehow turns every scrap of raw material into a finished product. Zero waste, zero leftover gas, zero inefficiency. Physics does not work that way. Not in any model anyone had ever constructed. The initial reaction from the scientific community was, in the words of one researcher, frankly alarm. Here is the part that should genuinely stop you. The iron web detected inside GZ9p3, forged inside stars that exploded over 13 billion years ago, drifted across the young, violent early universe and became the raw ingredients for the next generation of stars and planets. Our sun contains that iron. The Earth is built from those scattered elements. Your blood contains iron. Your bones contain calcium forged in the hearts of ancient stars. The carbon in every cell of your body was fused in nuclear furnaces that burned out before our solar system even existed. We are made of stardust from galaxies that, according to our best and most carefully constructed models of the universe, should not have been there. Then came something that looked, for a moment, like an answer. A graduate student named Catherine Chorosky led a study that re-examined the data on the most extreme galaxies Webb had found. She found that many of the apparently overmassive early galaxies were being fooled by their own black holes. These galaxies, nicknamed little red dots for their distinctive color and compact size, hosted black holes in their centers that were rapidly devouring surrounding gas. The friction from all that in falling material heated it to extreme temperatures, and that heat radiated outward as light, enormous amounts of it, blending invisibly with the light of the galaxy's actual stars. From billions of light years away, through Webb's cameras, a galaxy with a violently hungry black hole at its center looks almost identical to a galaxy with 10 times more stars. Webb sees brightness, and brightness is usually a reliable proxy for mass. Usually. Once the little red dots were removed from the sample, the remaining galaxies fit comfortably within the standard model's predictions. Relief. Stephen Finkelstein-Kwarowski's advisor was direct about it. There is no crisis in terms of the standard cosmological model, not from the galaxies at least, except, even after removing the little red dots, roughly twice as many massive early galaxies remained as the standard model expects. Not enough to break the model outright. Enough to leave a mark that doesn't go away. And then in early 2025, Webb found something that couldn't be explained by black holes or instrument errors. A massive spiral galaxy, quickly nicknamed the Big Wheel, that existed within the first 2 billion years of the universe. Spiral structure does not form quickly. It requires calm, orderly growth over long periods, not the violent, chaotic collisions and mergers that characterize a young, dense cosmos. Astronomer Themia Nanayakara said, "The galaxy either assembled its mass in an unusually neat and orderly way, or it formed most of its star in place, without the violent collisions that typically build galaxies of that size. Either explanation requires the Standard Model to bend." Meanwhile, a separate Cambridge team studied over 250 galaxies from the same early epoch and found the opposite pattern. Most of them were turbulent, clumpy, chaotic systems that had not settled into anything orderly. They looked exactly like you'd expect from a young, violent universe. So the early cosmos contained both messy, adolescent, unformed galaxies, and at least one remarkably mature, structured spiral, coexisting in the same slice of time. The Standard Model does not handle that contradiction gracefully. And then, the elongated galaxies. A study published in late 2025, led by Alvaro Pozo, and including researchers from MIT, Harvard and Taipei, found that many young galaxies observed by Webb appear strikingly stretched out, elongated, like cosmic cigars or capsules floating in the void. These prolates do not match predictions from the cold dark matter model, which is not just one ingredient in standard cosmology. It is the scaffolding, the foundational assumption upon which almost every other prediction rests. It determines where galaxies form, how they cluster, and what the large-scale structure of the universe looks like on the biggest scales we can observe. They do, however, match predictions from warm dark matter and wave dark matter, alternative models in which the filaments of the universe's large-scale structure are smoother, allowing gas and stars to flow along them in elongated streams. If dark matter particles are lighter or behave differently than the cold model assumes, the ripples from that change would propagate through almost every prediction cosmology makes. It would alter the mass of galaxy clusters. It would shift the expected distribution of dwarf galaxies around larger ones, a distribution that has already been a source of tension for years. It would change how gravitational lensing bends light around massive objects. You cannot swap out the foundation of a building and expect the walls to stay where they are. Professor Michio Kaku once framed it this way in a public interview. "We live in the Milky Way galaxy. It spins like a pinwheel, but when you calculate the rate of rotation, it spins too fast. It doesn't spin the way it's supposed to." So, astronomers threw their hands up and said, maybe there's a halo surrounding it that explains why it doesn't rotate like it should. But photographs show the Milky Way looks like a pancake, a flying saucer. Where is this mysterious dark matter? It's invisible. We are now postulating a new form of matter. Matter that weighs 10 times the weight of all ordinary matter. And if you could figure out what this invisible matter is, you could win the next Nobel Prize. Let that sit with you for a moment. The scaffolding holding the Milky Way together. We have never directly seen it. We inferred it. We named it. We built our entire model of the universe around it. And that model contains one more invisible ingredient that dwarfs even dark matter. Dark energy, the mysterious force responsible for the accelerating expansion of the universe, makes up approximately 68% of everything that exists. Dark matter makes up another 27%. All the ordinary matter, every star, every planet, every galaxy, every human being, every atom of every element on the periodic table makes up just 5% of the universe. We know what the 5% is. The other 95% we gave it names and moved on. One possibility that keeps surfacing as a potential solution to the Hubble tension is called early dark energy, a hypothetical burst of extra expansion in the first few 100,000 years after the Big Bang, which then vanished without a trace. Cosmologist Mark Kamionkowski described it as the universe receiving an unexpected kick right after it was born, a nudge that rippled forward through 14 billion years of expansion, slightly altering the rate we measure today. Nobody has detected early dark energy, but it is one of the only theoretical ideas that can close the gap between 67 and 73 without unraveling everything else the Standard Model gets right. There is also the S8 tension, A quieter crisis that most people outside the field have never heard of. The Standard Model predicts a specific amount of clumpiness in how matter is distributed across cosmic scales. When astronomers measure that clumpiness directly, they consistently find slightly less of it than the model expects. Not a dramatic gap, but a persistent one. Adam Riess calls it the little sibling of the Hubble tension. Two cracks, same wall. If both turn out to be real, they may be symptoms of the same underlying flaw. Two instruments in the same broken machine, each telling you something is wrong in its own quiet way. Here is what makes this moment in science remarkable. Nobody is panicking. The prevailing mood is not despair. It is closer to the feeling you get when you've been assembling a jigsaw puzzle for years. Confident you had the picture right, and then you find a piece that doesn't fit anywhere. It doesn't mean the puzzle is wrong. It means the picture on the box might not be the whole picture. And history strongly suggests that moments like this one don't end in failure. In the 1990s, cosmology nearly collapsed under a different contradiction. Measurements kept suggesting the universe was younger than its oldest stars. That made no sense. Stars cannot be older than the thing they live inside. The field was in genuine crisis. Papers were written. Careers were staked on competing explanations. Then came the discovery of dark energy, the realization that the universe's expansion was not slowing down as expected, but accelerating. And suddenly the whole picture snapped into focus. What looked like a fatal flaw turned out to be the shadow of something enormous that nobody had seen yet. The crisis didn't end the field. It advanced it by decades. New instruments are already being pointed at the problem. NASA's Nancy Grace Roman Space Telescope will conduct wide-field surveys designed specifically to map dark energy and probe the large-scale structure of the universe. The European Space Agency's Euclid mission is already gathering data, mapping the geometry of the cosmos on a scale no telescope has ever attempted. Future data from the Gaia Space Telescope will calibrate Cepheid distances with geometric precision, removing another potential source of systematic error from the base of the distance ladder. And the Atacama Cosmology Telescope has already produced the most detailed ground-based map of the cosmic microwave background ever made, slightly nudging the Planck estimate upward, though not yet far enough to close the gap. Not one of these tools alone will solve the Hubble tension, but together, over the next decade, they will almost certainly force a resolution. Either the Standard Model will be patched in ways that make it stronger, or it will be replaced by something better, something that explains everything the old model explained. And this too. You started this video thinking that James Webb was built to confirm what we already know. Now you know the truth. It was built to see further than we ever had, into the early universe, into the first moments after the Big Bang, to find the first stars and the first galaxies. And the further it looked, the more questions it sent back. Let me bring every thread together for you. The Hubble constant, the most fundamental number in cosmology, has two confirmed values, measured by two independent methods with two different telescopes, and they do not agree. James Webb was specifically deployed to resolve that disagreement, and instead, it confirmed that both measurements are accurate, meaning the problem is not in the instruments. The early universe contains galaxies that are bigger, more structured, more chemically complex, and more mature than the Standard Model says is possible at that age. Some of those galaxies, the little red dots, were explained by the activity of black holes. But twice as many massive early galaxies remain unexplained as the model allows. A massive spiral galaxy exists in the early universe at a time when spiral structure should not yet have had time to develop. Young galaxies appear stretched into elongated shapes that match alternative models of dark matter. Not the cold dark matter that forms the scaffolding of standard cosmology. Dark matter, 27% of the universe, has never been directly detected. Dark energy, 68% of the universe, cannot be identified, measured directly, or explained. We gave them names, that is all. A Nobel Prize winner, having exhausted every possible source of measurement error, looked at all of this and said on the record, "We have misunderstood the universe. This is not a failure. This is what science looks like when it reaches the boundary of what it knows and refuses to stop." Think about what you are actually witnessing right now. A species on a small rocky planet, orbiting an unremarkable star, in the outer suburbs of a mid-sized galaxy among hundreds of billions of galaxies. Using carefully polished mirrors and centuries of accumulated mathematics to argue about whether reality is expanding 6% faster than it should be, and getting genuinely, passionately, beautifully upset about it. That's either absurd or magnificent. I think it's both. The iron inside GZ9p3, forged in stars that exploded over 13 billion years ago, in a galaxy that had no right to exist as early as it did, drifted across the young universe and became raw material for the next generation of stars, planets, oceans, and life. You are built from elements scattered by impossible galaxies. Maybe that's the most important thing Webb has shown us. Not that our models are broken, but that the universe is far more generous with its complexity than we ever gave it credit for. Adam Rees said it in December 2024, carefully, as he always does. We have to take this problem seriously. 2 NASA flagship telescopes now confirm each other's findings. What's left is the possibility that we have misunderstood the universe. The universe isn't broken. Our map of it is incomplete. And the next version, whenever it arrives, is going to be stranger and richer and more astonishing than anything we have drawn so far. We are made of stardust from galaxies that weren't supposed to exist. Maybe that tells us something about what else is possible. Thanks for watching. See you in the next one.